Howdy folks, welcome back to CS 128 Honors. This is lecture 6, and today we're going to be covering ownership and borrowing in Rust. So we're going to be reviewing ownership at the beginning of this lecture. You guys should be familiar with it as Arul introduced it to all of you in the last lecture. And then I'm going to formally introduce borrowing. I know Arul also covered borrowing last lecture, but we're going to be diving deeper into it today. And then I'm also going to be introducing dereferencing in Rust. So this is a super important concept, especially when dealing with mutable references and pointers. That is a whole nother monster in Rust. So just introducing the basics of dereferencing today. And then I'm going to be introducing how to borrow with data structures. Okay, before we get into all of that, just a couple quick announcements. Homework 3 is due on the 20th at midnight. Homework 4 releases today and it's due on the 22nd at midnight. MP0 is due tomorrow, so make sure to get that in by tomorrow at midnight. MP1 releases today and it will be due on the 28th at midnight. I'll be releasing an intro video for that at some point, so stay tuned. Also, you might have noticed that the practice assignment goes live today. We'll be adding some more problems throughout the rest of the semester, so keep an eye out for that. And I'm sure we'll make announcements when those extra problems go live, but you can start to pick your way through that. Some of the practice problems contain hash maps. Hash maps are a concept we'll be introducing for MP2, so don't worry about those until we introduce MP2. Okay, let's get into ownership. So just to briefly review the 3 rules of ownership in Rust. Each value in Rust has a variable, and that variable is called its owner. And there can only be one owner of some value at a time. And when the owner goes out of scope, the value will be dropped. So what does this mean? Well, when we have this string s, s owns this string content hello. And then we enter in this new block of scope. We define w to be the string world, and so then we can do something with w, but once this little block of scope ends, if this was an if statement, a for loop, whatever it may be, w is dropped when it goes out of scope. So once we leave that scope of this little temporary block of code, once we leave that and then we exit the main function, well, s goes out of scope, and so this hello string is dropped from memory. Okay. And then just another example. So going back to this second rule, there can only be one owner of some value at a time. So at the start of our program, x owns this string hello. But then when we say let y equal to x, we're saying transfer ownership of this string into y. So if we tried to print out x, this line would not compile because x no longer owns the string. Y is the new owner. So we're allowed to print out the contents of y. We can modify the contents of y however we like, but we can no longer use x or reference x in any way because x has lost ownership of this string value. Okay. So one thing you might see is sometimes you're able to move ownership, and that can be kind of ambiguous. Well, that's due to this thing called the copy trait in Rust. So copy means you automatically transfer the data over and copy it instead of moving ownership, and this only works for primitive types. So let's say we have this variable x, and it is a primitive type, an unsigned 8-bit integer, set it to 5. Well, we're allowed to say let y equals x, and both variables are still valid. Due to the copy trait, we do not move ownership into y. So x still has ownership over this data. Y is also equal to 5 at this point, but they are different values of 5. So we can increment x by 1. We're allowed to do this because the data that was inside x is copied over into y. So when we print this out, x equals 6, y equals 5. Due to the copy trait, we are not moving ownership. And just once again, the copy trait is only defined for primitive types. So integers, floats, booleans, characters, etc. Okay. So there is this other thing called clone. So clone is this explicit function call to make some deep copy to a data. So what does this mean? Well, when we have some type that does not implement the copy trait, we need to be explicit and say .clone if we wanted to make a deep copy of it. So you'll notice here, we're making a deep copy of a primitive type, and that's valid because it implements the copy trait. But if we want to copy some non-primitive type, say a string, or your own struct, or your enum, we have to use this clone feature. So once again, clone is an explicit function call to make a deep copy of some data. So let's say we have this string hello, and then we move ownership. So y now owns this data, and once again, we cannot say x.pushStringWorld because x no longer owns this data. So this no longer compiles. And that is due to borrow of the moved value x. So the move occurs because we move ownership of hello into y. And then we're trying to borrow this data on line 5. More on borrowing in just a little bit, so hang tight. Okay, but we can use clone. So we have x refers to this data hello, and then we're going to say make a deep copy of x. So y also contains some data hello, but it's a different 2 separate copies of hello. And then we're able to modify x, and if we print that out, x equals hello world and y still equals hello. So if your data is not some primitive type, if it's something like a string, you have to use .clone if you want to make a deep copy. And if you move ownership, then you can no longer use the original data. Okay. So I want to go over moving ownership just once again. So remember, values can only have one owner, so this is invalid. We can no longer use x after having moved the data into y. And then, so just another example, something you might see in some homework assignments. So values can only have one owner, and if we move ownership to a different scope, say calling a function, that also consumes values. So in this example, we have this variable class, CS128 honors, and then we call this function say hello. So what happens here is we're moving ownership of this data here from the main, the variable defined in main into this function. So we're moving ownership from class to this variable name. So moving ownership of this data into here, we print out hello CS128 honors. And once name goes out of scope, once the function is finished, we're no longer able to access this data because it's dropped. So we're no longer able to call this function because class no longer has ownership of this data. So let's see a brief example of this. So if I try to compile this bit of code, we see here we're not able to compile it because a move occurs after calling this function. We move ownership of this data to name, and then name is dropped here. So we can no longer call the function because class no longer owns the data. Okay, we'll fix that example in just a little bit. Okay, so now I want to formally introduce borrowing and references. So an ampersand represents a reference, similar to C++. And references allow you to refer to some value without taking ownership of it. And so we call the action of creating a reference borrowing that data. So what does that mean? Well, at any given time, you can have one single mutable reference. So this means that with that reference, you can modify the original data that the variable you're taking reference from refers to. Or you can have an infinite number of immutable references using ampersand. So with mutable references, that means you can modify the original data. With immutable references, you cannot modify the original data, but you can read it. And one thing to note is mutable references must be a reference to a mutable variable. So if you have a mutable reference, if you want to take a mutable reference, you have to say let mute variable in order to declare that mutable reference. So you cannot make a mutable reference to an immutable variable. And like a rule mentioned in last class, references must be valid. So they must be references to valid data. So let's see this example here. So we have this mutable string x. X refers to this hello string. And we can take a mutable reference to x using this ampersand mute. So we're not moving ownership. We're just saying that y now refers to x, and y can change what x refers to. And then if we try to modify x, well, we're unable to do that. So what this push string function does is it takes x as a mutable reference, and it tries to modify it. But because we can only have one mutable reference at a time, we're unable to do this. So since y already has that one mutable reference to x, and so this would not compile. Okay, let's go ahead and fix our examples. So we mentioned here that we're moving ownership out of this main scope, moving ownership of this data into the function say hello. Well, what if we just borrowed it? We don't want to modify the original data. We just want to print it out, and that's it. So what we can do is we can create a reference to the original data. So rather than consuming ownership, rather than taking ownership, we'll say name is now just a reference to the original data. And then we're going to print it out, and then we're all done. And the original string remains after this function. So if I said, say hello borrow, and then I create a reference to class, then this function only borrows the content of the string immutably. It's not able to change it. And then class still owns this data. So there's no longer this error here. So one thing to note, though, is say hello still consumes this data. So once we pass class to say hello, name now takes ownership of the string, and the data is dropped here. But we can, call say hello borrow twice, and well, there you go. And so now our code will compile. Okay. And so one thing I also want to note is with strings, whenever you borrow a string, you can interchangeably use ampersand string or ampersand str. To Rust, they're the same. When you try to compile your code, the Rust compiler will know that you're using a reference to some string data. Under the hood, they're somewhat similar. The next lecture will cover how this works. But I just wanted to point this out. If you take a capital S string like this, and you take a reference to it, it can be converted to an ampersand str automatically in a function. Okay. Okay, on to dereferencing. So if you have a mutable reference to something, then you can change that data using a star before it. This is very similar to C or C++. If you have a pointer, then you can change the data that pointer points to using a star. Because references are, in essence, memory addresses. And like C and C++, if you dereference a memory address, you can change the content of that memory at that address. Okay. Let me briefly go over an example of dereferencing. So if I have this string, CS128 honors, and I make this variable mutable, well, what I want to do now is let's take a mutable reference to it. So let some, let's say x is an ampersand mute string. Okay, and what I'm going to do is change the contents of my class variable. So what I can do is say ampersand x equals a different string. So string from, like that. So what I'm saying here is create x. X is some memory address, a valid memory address because it's referring to class. And I'm going to change the content at that memory address. So what ends up happening is when I print out class, this will now just print out x. So build that. There we go. So I went into this memory address, changed the content to the string x, and then printed it out. So kind of tricky, but very similar to C or C++ if you're familiar with that. In essence, like once again, references are just memory addresses. They're valid memory addresses in Rust. So I can go to that memory address, dereference it, and change that data content that that reference refers to. Okay. So dereferencing can be somewhat tricky in Rust. There are cases when you have to do it and cases when you don't have to do it. So you need to dereference mutable references to primitive types. So if you have an integer, you take a mutable reference to that integer, you have to dereference it if you want to change it. I'll show you an example of this in a little bit. You have to dereference when using iterators. Once again, I'll show you more on this later. You do not need to dereference when using bracket access on vectors. Once again, I'll go over more examples in just a little bit. So if you have a custom function for you implemented on a type like strings, you do not need to dereference the data. So all you need to do is pass in a reference and that function call will handle it for you. So if we go back into our example, we have this this mutable string class here, and we can say class.push string. So what this will do is we don't have to dereference class, but this push string function will modify the original content, will modify this data here. So push string under the hood will dereference this memory address, modify it, and then continue the program for you. And so we'll cover more about mutable references and non-primitive types in future lectures, and exactly how that function call without dereferencing works. So stay tuned. Okay, we just showed you how to do that. Okay, so now I want to cover ownership in data structures. So let's see. We know that some values can only have one owner, right? So what happens when we add elements to a vector, right? We have some piece of data, and then we're just sending it off to the vector. Well, the vector will now own the value once we add it to that data structure. So if you have some piece of data that's living in some scope, and you try to add it to the vector will take ownership of it. If it is not able to take ownership of it, it will clone it. So it has ownership of the cloned data. So when we try to access a value from a vector, we're given a reference to it because the vector owns that piece of data, and it's not going to give that ownership to you. It needs to retain that data so it can be used in the future. So in this little example here, we have this vector of strings. We cannot move ownership of this 128 into this new variable because the vector owns every single piece of data inside it. We cannot transfer ownership of this component of the vector to a different variable. So this errors out. And so sometimes you'll see this cannot move because the value has type blank, which does not implement the copy trait. Well, this goes back to copy clone. You cannot try to do this move ownership thing because you cannot make a deep copy of the variable implicitly. You have to call .clone if you want to have this declaration here. So I would say let element equals x2.clone. Okay, let's go into ownership and vectors. Okay, so this code is a lot, but I will slowly walk through it. So I have this mutable vector food here, this vector of strings. And then I'm going to take this first element here and try to modify it. So I'm saying let pizza be a mutable reference to the first element of my vector. So I take a mutable reference using ampersand mute. And I'm referring to the element at index 0. And then I'm going to say push string. So modify this data, add some exclamation marks to it, and then print it out. Okay, and then I'm going to take a immutable reference to the element at index 1, and then add it to another string s. So I want to point out, because this is an immutable reference, I cannot change it. So I cannot say, let's see, ice cream dot push string exclamation mark. This errors out because it is not a mutable reference. It is an immutable reference using just an ampersand. If I change that to ampersand mute, then that would be possible. But because it is not, this statement doesn't compile. Okay. And then down here, I have a bunch of sort of iteration methods. So there are a bunch of different ways to iterate over data structures in Rust. I'm going to go through how to do so for vectors, and you're going to be using this in MP1 a bunch. So there's this function iter, then iter mute, and into iter. So what iter does is it will iterate over your vector and give you references to each element inside of it. So f is a reference to a string, reference to each of these, and all we can do is print it out. We're not allowed to change it. Okay, and then iter mute, this gives you mutable references of each of the pieces of data inside my vector. And once again, if I want to change those, I need to use a dereference. So I'm dereferencing this mutable reference and then changing it to a different string. So this little syntax here is quite interesting. Similar to the way you use println, you can use this format macro. Format will just return a string. So rather than printing it, you can assign it to a new variable. So it's used the same way println is, except it generates strings. Okay, finally, we have into iter. So into iter will consume the vector. It'll take ownership of the vector and therefore take ownership of the pieces of data inside of it. So we now have ownership of each piece of data, and we can do as we like. The thing to note, though, is if we try to use food afterwards, our program will not compile, because into iter takes ownership of food. So try to stick to iter or iter mute, because into iter consumes all of the data, and you're no longer able to use it after that. So this will not compile. We try to compile it. We'll get this error, value borrowed here after the move, because food is moved, or the ownership of the vector is moved from food to the function into iter when it's called. So we have to comment that out, and then our code will run. So let's go through it line by line. So here we took a mutable reference to the element index 0. We added some exclamation marks to it, and there we go, they show up there. And then here we took an immutable reference to the element at index 1. We added it to a string, printed that out, so I like ice cream. And then in this for loop, we went ahead and printed out all the contents of the vector. Remember, we changed the contents of the index or the element index 0, so that's why each subsequent for loop has exclamation marks in it. And here we modified each of the pieces of data inside the vector. So we're printing out yummy before each string. Finally, we consumed the vector here with our iterator, so we're no longer able to use the vector after that. Okay. All right, so these are a couple of ways to access data in vectors. These will come in handy as part of MP1. So you have this bracket notation that you might have seen me use. Whoops. There we go. So we have this bracket notation to access a element at some index. So you're going to try and take ownership, or rather try and copy the value at index I. If you're unable to copy it, well, then you have an error. So you got to clone it. Okay. And then if you have an ampersand before it, you immutably borrow the value at index I. So you're not trying to take ownership. You're just saying, I'm referring to some piece of data that the vector owns. And then ampersand mute, mutably borrow the value at index I, and then you can modify the data inside the vector with that. One thing I should note is that because you're using bracket notation, if you try to pass in an index that's out of bounds, your code will crash. Your code will panic. So there are some safer methods, like the get method. Briefly, if you try to take a mutable borrow of some vector, your vector must be declared as mutable. Okay, so .get, well, you try to get an immutable reference to the index I, but you'll get an optional type. So what the option does is if you pass it an index that's out of bounds of the vector, say you have a vector of length 10, try to access index 20, you'll get the none type of the option. If you are able to access that particular index you pass in, you'll get some with the data inside it. The data inside is a reference to the original data inside the vector. Okay. There's also get mute. This gets you an option with a mutable reference to the data at index I. And once again, your vector must be declared as mutable if you try to call get mute. All right, and this is a review of the code example. Iterate over the vector using immutable references, mute, iterate over the vector using mutable references, and into iter, try to take ownership and iterate through the vector. And like I said, you can no longer use the vector after calling this method on it. Okay. I want to quickly go over a final example. So when using vectors and using iter-mute, you have to dereference the iterator variable if you want to modify the original content. So if I have this mutable reference to every element in my vector, I dereference it if I want to change it, and I dereference it if I want to add it to some value. So this little dereferencing here is interesting. If you have an immutable reference, then you do not need to dereference it, but because it's mutable, you have to dereference it. It's a subtle sort of difference in Rust. You're not able to add a type with a mutable reference to a type. I'm not entirely sure why, but it is something you have to watch out for in Rust. So when in doubt, try dereferencing, and that might fix your problem. Okay, so we're going to go through each piece of data, dereference it, change it, add 2 to every one of these, and then move on. And then here, I'm going to dereference that data, multiply it by 2, and then move on. Okay. The thing I should note, though, if you use bracket notation, you do not have to dereference. So if I'm going through by index, I can take each element at index I, increment it by 1, and my code will work fine. So slight distinction, the dereferencing happens under the hood here, so you don't need to worry about dereferencing if you use index notation, but iterators are at least my preferred way of going about things. Okay. So if I am not modifying my data, I do not need to dereference it. So you might have noticed the code compiles both with that little dereference and without, because my data is immutable. So it does not matter whether or not you have this dereference in there if you have just immutable references, because Rust understands to do this under the hood. So if I run my example here, so we go through each piece of data, add 2 to it, then we go through again, multiply it by 2, finally go through once again, and then add 1. And then at the end, we sum it up and print that out. All right, that's all, folks. Another long lecture again. Thanks for hanging in there. And just another reminder, you have assignments due today and tomorrow, and MP1 also releasing today. Take care.